Hello, everyone. I hope everybody's still doing well. I wanted to go ahead and get uh, the second lecture of the week done. And as I said before, what's left with this week uh, is the topic of rational functions. And when you took your college algebra class, you spent some time on rational functions. So basically, we want to review that and maybe talk about a few concepts that you may not have covered. It really just depends really on the length of time that you spend on the topic. So what we want to do to finish up this week on the polynomials is to take what we know about polynomials and transfer that to a rational function, which is defined in terms of polynomials. So I want to do some definitions with examples and then see how all of these are related where we think about intercepts, where we think about zeros, things of that nature. So let me go ahead and share my screen. Now, when we actually do this, we have to think in terms of polynomials. So what is a rational function? Well, we think of a rational function, we'll just use an r of x, and I'll use a notation that Dr. Larson does in his calculus book. It's actually a useful one. I sometimes use it, but we could just say the numerator n of x divided by the denominator d of x, where n and d are polynomials. So we spend a lot of time with the polynomials, and this really does take up a lot of time in more advanced algebra courses. Polynomials are really important objects. And so what we could do is we could think of polynomials in terms of their general form. So we could say n of x would be a sub n times x sub n plus a sub n minus 1, x sub n minus 1. And then we'll just keep moving down to the first degree term and then the constant term. So of course, n would have degree lowercase n. So remember, a polynomial of degree n is always going to look like this. That is, we are assuming that the leading coefficient a sub n is non-zero, as we always do. And then, of course, d of x could be written, and we don't necessarily have the same coefficients. So we could say b sub m x to the m plus b sub m minus 1 x to the m minus 1. And of course, we can descend to the linear term b1x plus b0. And here, of course, the degree of the denominator polynomial would be m by definition. Now, when we think about rational functions, we can do all the things we normally do with any function. We can think of range and domain. We can think of x-intercepts, y-intercepts. But there are two other objects that we haven't usually discussed in the past, especially with polynomials, and they have to do with intercepts. So as before, we discuss number one, domain, range when it's suitable, x-intercepts, y-intercepts, and of course, we already know we can think of BV technique. So BV technique for sign test. Now, there are two new items. There are two new items. these are actually termed asymptotes. Number one, we have the vertical asymptote. Oh, too many S's. Let me get rid of this. Asymptote, and then P, tote, asymptote. So we'll start with this one. Now, when you say asymptote, you think of the adjective asymptotic. That is, an asymptote in what we're going to be talking about will be either a vertical line, a horizontal line, or a line with non-zero slope. That is like maybe something like y equal x plus 2. So these objects will be asymptotes. And the reason they're called asymptotes is that the graph of the rational function will arbitrarily approach these objects. That is, that when you say something's asymptotic to another object, they get really, really, really close together. And so the asymptote is going to be a device that we use to sketch the function. It's not going to be part of the function, but it will be a device to help us sketch the function. So let's look at a definition. So we would say the following. The vertical line x equals c is a vertical asymptote of the function, and in this case, we're talking about the rational function here, of the function r of x, if and only if, and this is important, the limit as x approaches c, and we'll do plus for the right of r of x, equals plus or minus infinity, or, and this is an inclusive or, it could be both, and it usually is, the limit as x approaches c from the left of r of x yields plus or minus infinity. Basically, ladies and gentlemen, what that is saying is that the function values become unbounded. So we would say the function values of r of x become unbounded. So the idea is that when we say something is plus or minus infinity, if it diverges to infinity, then it just gets arbitrarily large. If it diverges to negative infinity, then it becomes arbitrarily small. So again, we don't look at these as being numbers. We just look at these as being behaviors. The function's diverging. It's becoming infinitesimally large, or the function diverges, it's becoming infinitesimally small. So you might be thinking, okay, these must be like calculus notations, and they are, but they're very intuitive. So basically what we're saying is that when we have the C, if we do the plus approach here, we're approaching from the right. If we have the minus in the superscript, we're approaching from the left. So this is left approach, this is right approach. And this is just a standard notation. I just want you to think about what's happening. We're approaching C usually from either side. And all we have to have is just one of these occurring. And I've got plus or minus here because that's going to depend on the function and the BV technique. Basically, doing a sign test. The sign test will say, well, we affix a plus to the infinity or a negative. So that we already know how to do, but now we need to figure out, how do we figure out these vertical asymptotes? So let's talk about that. So when you say that the vertical line x equals c is a vertical asymptote, how do we come up with the c? And it's actually pretty simple. we define vertical asymptotes or actually, I just defined it. Let's just say what we're actually doing. We determine, let me give a little bit more room. We determine, and actually it's really the same thing. We determine, we define, but I think determine probably is a little bit better. It's like, how do we go about it? What's the procedure? We determine vertical asymptotes of R of X, and I'll write out what it is, N of X divided by D of X by computing all zeros, if they exist, of D of X that are not zeros of N of X. So basically, it's like we're doing a domain calculation, but we're not interested in zeros of D that are also zeros of N, because that would just be a hole in the function. And we've already talked about that. So we're only interested in the isolated zeros. So again, when we look at this, we think about having a C and maybe a little interval about it where we know D of C equals 0 and N of C does not equal 0. And then for, and we'll just call this A to B, for X element, and we'll say A to C union C to B. So we're going to just kick out C here. For these X, D of X and N of X will both be non-zero. So when we're close to C, the only zero that we want is D of C. We want that to be 0, but everything else is non-zero. So this is what we call an isolated zero. And many of them are anyway, because we're considering the entire real line. And so we can get as close as you like to see from either side. So we can approach from the left and we can approach from the right, as long as that's in the domain of the function. So again, in general, computing vertical asymptotes just means, well, can I figure out zeros of the denominator? And in most cases, the computation will be relatively straightforward. So for instance, here's an example. So we have R of X equals X plus 3 divided by X squared plus 5X. So when we look at this, we first see that this is a ratio of two polynomials. And if, while we're at it, we might as well get used to this. The degree of the numerator is 1, and the degree of the denominator is 2. So we think, okay, let's just go ahead and factor this and figure out the zeros of the denominator. So we have X plus 3. And then downstairs, we have X times X plus a 5. So when we look at that and we think about zeros, we just think about zero factor law. So by the zero factor law, or the zero product, we just basically see that if X is 0 or X is -5, we get zeros. So for instance here, we'll say, let's go ahead and notate this just like I did right above it. Say this is N of X, D of X, just to bring the point home. And we see that D of 0 equals 0, again, X equals 0, and D of -5 equals 0. However, N of 0 does not equal 0, and N of -5 does not equal 0, which is what we need. So basically, when we're close to both of these numbers, That is, we have -5 and we think of a little interval about them, and we have the number 0 and a little interval about that. The only place where we get a 0 will be at D. Everything else is non-zero, away from the -5 and away from the 0. And that's the idea that I was talking about right here. So to make it short and simple, we just make sure that we find zeros of D that aren't zeros of N. And then we have a vertical asymptote. Now, when you get to calculus, you'll talk more about the limiting process and basically why the function becomes unbounded, because you will define what it means for a function to become unbounded. That's a calculus topic. So what we try to do in pre-cal is to set you up with all the preliminary information so that when you see it in the calculus textbook, you're going to say, oh, I know what that is, or I know that notation, and I've heard the term vertical asymptote. So we're just trying to build the foundation so you, when you get to calculus, you can proceed to the limiting concepts that will take your knowledge even higher. So what we want to see here is if we wanted to check here, okay, what's going on plus or minus infinity? So we do the BB technique, but notice we also have to consider the zeros in the numerator, which are -3. So D has a 0 at -3, and it's important when we're trying to determine sign. So the sign of R of X will determine basically what sign we affix to the infinity symbol. So let's go ahead and write it down. Now notice, when we look at all of these zeros, they're all multiplicity 1. They only occur with multiplicity 1. So that's going to help us with the sign test really nicely. So again, we've got the -5. We've got the -3. And we have the 0. So now what we want to do is basically just test the sign in one place. Then we can use the multiplicities, because we know in all of these cases, the sign's going to change. We don't necessarily cross through a point where the function is undefined, but because the multiplicity is 1, the sign will change, but not in the sense of crossing it. It's just like we stop and then we hop over it, because that's it's like a black hole, so to speak. In hopping over it, do we really do that? So for instance, let's take some simple numbers here. Like for instance, like a -10. So if we check that, the x plus 3 is negative, the x is negative, and then of course the x plus 5 is negative. So 3 negatives make a negative. So that means we're below. Now, of course, if we're below, we will change sign at -5, we will change sign at 0, and we will change sign at -3. And -3 is really the only place where we actually cross. So I'll do something like this. So up to here, and then we actually cross through. And then of course we break and we're like this. So I don't want you to think that we're actually crossing, because these are not places where the function's defined. But notice now, by the multiplicity argument, we have plus here, we have minus here, and we have plus here. So now we can approach from either side where we have vertical asymptotes defined and write down the plus or minus infinity. So now we can see the limit as x approaches -5 from the left, in this case, of R of X, and I'll just write R of X, it's right up here, R of X, that will be negative infinity. And then, of course, the limit as x approaches -5 from the right-hand side, will be the plus infinity. So it's really, and you don't have to put the plus with the infinity. I do it if I do plus or minus, but just infinity is fine. And then of course we can do the same for 0. The limit as x approaches 0 from the left of R of X, again, will be negative infinity. And the limit as x approaches 0 from the right, again, the sign is positive above, will be positive infinity or just infinity. So when we do some sketches, we will just allow the function graph to approach the vertical line. But of course, if it's infinity, we approach from above the x-axis. If it's negative infinity, then we approach from below. So this just helps us to negotiate the proper signs. So even when you get to calculus, you'll still be doing the BV technique. You'll still be testing sign. It's just that you're going to add more information so you have more detail as to what you're really doing. Okay, so vertical asymptotes, again, for a rational function, they're zeros of the denominator that aren't zeros of the numerator. That means they're isolated. And so when you're just doing a basic problem to identify vertical asymptotes, approach it that way, just like you're doing a domain example. Most times students say, well, I'm getting the same answer as I would for the domain. Basically, what they're saying is that the numbers that you eliminate basically determine the vertical asymptotes. So now let's just kind of write to the side here, the VA. Now that we're professionals, we'll just call them vertical asymptotes. We know we have x equals 0 and we have x equals -5. So we made sure everything made sense, but now we have to remind ourselves, what is the vertical asymptote? It is a vertical line. So when you notate the vertical asymptote, you must draw it correctly or write it correctly. X equals 0. You can't just say 0. That makes no sense. A vertical asymptote is a vertical line. So it must be written as an equation. So many students make this mistake and get so confounded. And I'm like, well, you can't, you have to describe the object as what it is. We focus so much on the sign and identifying the actual value of C, but we finish it off, like I said before, as I've written here, right here, the vertical. And of course, I should have put the line there. How funny. I always say the word, but forget to write it. So it's the vertical line, X equals C, right here. So that's how we describe the vertical asymptote. We write it as the line that it actually is. So the vertical line. So BAs are fairly straightforward to compute. We do a sign test to figure what sign we append, just like we have been doing. And then when we sketch our graph, and we'll do some examples, we know exactly what it should look like, and to give a reasonable graph. Okay. Now, what we want to do is look at the second object. The second object is again an asymptote, but now it's a horizontal. So we'll say, in this case, I'll write line this time. The horizontal line, y, and of course we can call it C again, as the value C, y equals C, is a horizontal asymptote of the graph, again, of the graph of R of X, the rational function, of the graph of the function R of X. And of course, it doesn't necessarily have to be rational. It could be another type of function, but we're studying rational here, of the function R of X, if and only if. So again, let me repeat, the horizontal line y equals C is a horizontal asymptote of the graph of the function R of X, if and only if. We have two more limit ideas. That is, we can say the limit as X approaches infinity. That is, now the values of X will get arbitrarily large, and this will equal C, or, and this is an inclusive or, one or the other or both, the limit as X approaches negative infinity of R of X is also C. So in most cases, both of these will be occurring, but you only need one to have a horizontal asymptote. So the idea is, okay, isn't this interesting? So when we did the vertical asymptotes, we just basically look for zeros in the denominator that aren't zeros of the numerator. So how do we figure out the C part for horizontals? So we have to go back to how we define N and D basically as polynomials. So here's how we figure out. Okay, so how do we determine these asymptotes? So basically we have to look for these limits. And then of course the limit here will define the horizontal line. So let me just say this again. A horizontal asymptote is a horizontal line. It is a horizontal line. And so when you type it or write it, you can't just say C. That makes no sense. It is a line. So you must write or draw the equation. You know, when we do mathematics, we're drawing, we're making art anyway. So make sure you write an equation. Okay, for case one. Now, just to think about this, remember R of X equals the numerator polynomial divided by the denominator polynomial. And so in the first case, we have if the degree of N is strictly less than the degree of D. That is, the numerator degree is less than the degree of the denominator. Then this implies that the limit as X approaches infinity of R of X is 0. So, or we'll get, well, you know, maybe I could do plus or minus. I'll do this too. Just go ahead and write them out. Remember, it's an inclusive or, one or the other or both. So in this case, this defines the C. So horizontal asymptote, there's the C, and we just append the y equals 0. So there's no computation to do here except to notice that the degree of the numerator is less than the degree of the denominator. If that's true, then as X becomes large, either positively or negatively, the numerator basically relative to the denominator. And so that's why we get a limit of 0. So that's a really easy result and something that you'll be able to prove in calculus. At least now intuitively, it makes sense to us. If we think about the last problem we did, that was case one, because we had the degree upstairs was 1 and the degree downstairs was 2. So this would have been the horizontal asymptote. Okay. Now, what's the next case? Degree of N equals the degree of D. Well, this just implies, now remember how we define these, the limit as X approaches infinity of R of X will now be the ratio of the leading coefficients. So we'll have A sub N over B sub M, or the limit as X approaches negative infinity of R of X will be A sub N over B sub M. So basically here we have N equals M. And this is where students say, oh, the ratio of the leading coefficients. The idea is that when the degrees are the same, the X values basically absorb. And the only thing that's kind of left living is just those ratio of leading coefficients. And so that makes for an easy asymptote. So now this implies the horizontal asymptote is just Y and the ratio of the leading coefficients, A sub N, B sub M. And in this case, of course, M and M are equal because the degrees are the same. So again, in case one and case two, we actually get a line that has 0 slope, horizontal. Now, as the degrees start to change, that is the degree of N. Now you're thinking it's always been less or equal to. Now what happens is the degree of D actually surpasses that of N. Well, we don't get any more horizontal asymptotes. And of course, we could spend a lot of time on this. But what we're going to do is look at the case where the degree of D is one more than the degree of N. So here's case 3. And this is a special case. We've already done the horizontals. We won't get horizontals for anything else. So we'll say the degree of N is 1 plus the degree of D. Like I said before, one more. Now, in this particular case, we get what we, and this was interesting. I was thinking about writing this up with, oh, I dropped the paper. Writing this up with some limiting definitions, and there are times when things are useful and times when they're not so useful. So the idea here is that we're thinking that how are we gonna come about this? Okay, we're thinking if we do some polynomial long division, if the degree upstairs is one more, then when we divide, we're going to get a linear part and then a rational part. And so in this particular case, in order to actually find the asymptote, we have to use polynomial long division. So I'll just say this implies no HA, no HA. We get a slant, or sometimes called oblique asymptote. So basically what we're saying equivalently, we're saying that the limit as R approaches infinity, or excuse me, not R, X approaches infinity, gives some linear function, and we can think of it as maybe mx plus b, or the limit as x approaches negative infinity of R of x gives us some linear function mx plus b. Now, when we think about it, we start to think, okay, well, what's the m going to be? We can write down what m is, where m will actually be, in this case, a sub m plus 1, because it's going to have one more, divided by b sub m. Because again, the degree of the numerator will be one more. So basically, again, ratios of leading coefficients. But we know exactly what the m's going to be, and the rest of it, we just have to finish off the polynomial long division. So we get that much. And so like we see, what we see here now, let me go over here. The slant asymptote or oblique asymptote, your choice, is a linear function. It's a line, a linear function. We compute this by polynomial division. And if it's really simple, maybe we can use synthetic. Polynomial division. So I actually derived a general formula for some special cases, but it's more haphazard to try to remember the formula than just do the computation. So let's look at some examples here. So first off, say we go back to the example we did first. R of x equals x. If I recall, I think it was an x plus a 3. Yes, x plus 3 divided by x squared plus 5x. Well, we see the degree of n is 1 and the degree of the denominator is 2, d of d. This is case 1. Degree And if you like, you can just call this one n of x and call this one d of x. Degree of n equals 1, which is less than the degree of d, which equals 2. So this implies y equals 0 is the horizontal asymptote. So again, that really makes the graph simple. You don't have to really worry about it. And then of course you can use the sign test to figure out where the graph is relative to the x-axis, above or below. The sign test is so valuable because it just orients us as to where we position the actual graph. It's a very valuable technique, and we get a whole lot of reward for a little bit of effort. So here's an example that we've done. Now say we have r of x equals, here's an example from your WebAssign. Let me look at this. So we have something like this: 3 of x plus 6 divided by negative 6x plus a 2. Now, when we look at this, here's the n of x and here's the d of x. But these are both of degree 1. So we have case 2. The degree of n equals 1, which is also the degree of d. Now, you don't have to, call everything n and d. You could just, write it out this way, but I'm thinking just making a notation, or you could just say, right to the side, degree 1, degree 2, or whatever the case may be. Here we've got degree 1, degree 1. Here we had degree 1, degree 2. And so now when the degrees are equal, we get the ratio of leading coefficients for the horizontal asymptote. So now we have y equals, okay, the leading coefficient of n is 3. The leading coefficient of d is negative 6. So we get, if and only if, y equals negative 1/2 as the horizontal asymptote. Okay? So when it comes to horizontal asymptotes, pretty straightforward to compute. You often are glad when the polynomials are written in descending form. Sometimes they may be factored, and you have to do a little bit more work to multiply all the x's together to get the leading coefficient, but that's doable. Again, we have to be happy for how the problem is given to us, especially if it already takes a little bit of work away from our plate. Now, let's look at the oblique case or the slant case. Say we have something like this. And here's, I'm looking at these WebAssign problems because we're going to graph them. Here's an example. So we're going to go ahead and do some work before we get to them and then come back and refer. So in this particular case, again, we have the n of x and we have the d of x. But note, in this case, the degree of n is 2 and the degree of d is 1. So we've got case 3, which says degree of n equals 1 plus degree of d, which is 1 plus 1, which is 2. So again, the degree of the numerator is 1 more than the degree of the denominator. And that gives us the slant asymptote or the oblique asymptote. But like I said before, we can just use polynomial division, but this is even easier because that's a c, x minus a c. So we can use synthetic to figure out the linear part. So let me show you how that works. Again, you can always use the standard division, but if we can use synthetic, that's quick. So let's just go ahead and divide. So we have 1, negative 2, negative 24, and we have a 7, of course. Bring the 1 down. 1 times 7 is 7. 7 plus negative 2 is a 5. And then 5 times 7 is a 35. 35 plus a negative 24 gives us an 11. So those numbers were easy. But now we see, okay, when we divide here, we get x plus 5 plus a remainder of 11. Well, clearly this doesn't divide. You know, it's like, okay, 7 is not a zero of the numerator, but we weren't thinking that it would be. So the idea here is that when we look at this particular example, we now have the linear part and we have the nonlinear part 11 that will go with the denominator here. So this implies by division that r of x is the linear part, x plus 5 plus the remainder. But again, when we look at it this way, we're saying plus 11 divided by x minus 7. Because remember, r of x is x squared minus 2x minus 24 divided by x minus 7. So this is kind of like the alternative form. We've got the fraction here, so we're dividing everything through by x minus 7. So the quotient part here gets lost, or the divisor part here gets lost, and we're just left with the quotient. And then, of course, the remainder gets stuck with the divisor. So this is that alternative form I was telling you about. So now you can see that this is really a good way to actually consider the case where the numerator degree is one more than the denominator. Why? Because now it reveals the linear part, the slant asymptote, and then the nonlinear part. So you can see as x gets very large, this particular term becomes closer and closer to 0, and the function values approach x plus 5. So this implies that the slant asymptote, and we'll just say slant asymptote for short, will be y equals x plus 5, right there, slant asymptote, y equals x plus 5. And of course, you always get the slant asymptote by division. And if it's simple enough that you can actually do it by synthetic, then do. Of course, if it fits the hypothesis of synthetic division. The only thing is, don't use synthetic when it doesn't work, because you'll just get nonsense. Okay, so now let's take some of these ideas and basically put them into graphing a rational function. And we'll include maybe the BB test and the x and y intercepts to get a reasonable graph. So let's start with, we'll start with the one that we actually worked on that had the horizontal asymptote, and we'll just finish it. So we want to graph this. So in this case, we have r of x equals 3x plus 6 divided by negative 6x plus 2. Now, I'm going to go over here. We already have HA. We got y equals negative 1/2. We've already computed that, so we'll go ahead and put that down. Let me make this just a tad bit less bright so it doesn't flush out at the end, and refocus. Now, if we look here, we can go ahead and rebrand this a little bit. We found this. Let's go ahead and factor the numerator. So we'll get 3 times x plus 2. And downstairs, factor the negative 6. So we get an x. And of course, that's minus a 2 divided by 6. Again, we have to divide by the negative 6. So we get 3 times x plus 2. And then we have a negative 6 times x minus a third. Okay, so that's just isolating zeros in the denominator. So now we're thinking, depending on what we're looking for, we look to the expression that's the most convenient to find it. So now we can see, okay, 1/3 is a 0 of the denominator. So we have a VA. Again, we know it's a VA because it's not a 0 of the numerator. So we have x equals 1/3. Again, remember, ratio of leading coefficients, isolated 0 of the denominator. a 0 here that's not a 0 upstairs in the numerator. Now x-intercept. X-intercept, we just look for the zeros of the numerator. That'll be a -2. And then y-intercept, that's just r of 0. So we say r of 0. Of course, 0 is well defined here. We just get what, 6/2, which is 3. So we've got a lot of free stuff. We have a lot of simple material. And now what we want to do is just get a relatively simple graph. Do we have to work hard to get it? Do we need a sign test? I don't think we're going to need one, but let's just go ahead and verify everything. Note, sign tests are quick to do. So when we do the sign test, we have to use the places or the real numbers for which the function's undefined and the real numbers for which it is 0. So again, just like we had before, the BBs. So we have a -2 and we have a 1/3. So if you like, just go ahead and do a -10 here and just look right here upstairs. So the -10 here, that's going to be negative. And then of course the -10 in this case, we have negative here, negative. So negative times a negative is positive, overall negative. So this is below. But notice these are all multiplicity 1. So we cross through here, positive, and then this way. Of course, no crossing there. That's a vertical asymptote. So we have negative plus negative. So now we can draw it. Just go ahead and sketch in our asymptotes. Put in our intercepts. And then we can use the sign test to get the correct orientation of the curve. So we'll spread things out a little bit. Let's just say we've got the 1 here. So we've got a 1/3 about right here. So there's our vertical asymptote, just to spread it out some. And we can dot the asymptotes. We can never cross a vertical asymptote, but horizontal asymptotes, it is possible to cross a horizontal. And then of course, for the horizontal, we've got -1/2. So we'll do the 1 here. So about right here. So we have y equals -1/2. And then we have x-intercept of -2. Oh, sorry, negative x, but help to be on the x-axis, right? So about right here. -2. So we've got that, and we have a y-intercept of 3. So here we have a 1, a 2, and a 3. So now what we're seeing is we have to hug this line at -infinity, pick up the intercepts, and then hug the vertical line. So again, below, above, below, above, below, and then just move on up here, pick these up, and then hug again. So we always hug the asymptotes, below, above. And now over here, we have to hug, again, from the negative here, -infinity, but then we don't cross. We have to hug the line here, and we don't cross the horizontal asymptote. So we get something like this. So again, when we think about these graphs, and of course you're thinking, well, that looks 1-to-1. Well, it's not 1-to-1 because the graph, I mean, it is a 1-to-1 function, and I've shown you how to prove that. That's not hard to do. But the idea is that this graphing procedure, except for the calculus part, it does tell us a lot, and it's a reasonable graph. So in calculus, you'll be able to prove that this function is always increasing, and you'll be able to prove the so-called concavity that we kind of drew in, but we really didn't know why. We know we have to hug, and we have to have a nice smooth curve. So the idea here is just with pre-calculus techniques, we can do quite a bit of work towards a reasonable graph. And then when you get to the calculus, you'll add the finishing touches, which will allow you to have much more precision, especially when you have, in this case, maybe you have some concavity arguments, or in another case, you might have extrema, like a relative maximum or relative minimum, which again, the pre-calculus would not uncover, but the calculus techniques with the derivative definitely would. Okay, so we see here that even though we've got the sign test, we probably could have figured it out, but this is just a nice check for this. So we get a nice graph for, not too much work. So let's try another one. So let's look at another example of a rational function. So it looks like intercepts, asymptotes, sign test, maybe some symmetry, if it exists. I always say if it exists, because that's a big if, right? So here we have r of x equals, say we have negative x divided by x squared minus 16. Again, I'm trying to mimic the first one that I did, but I want to see if I can get some symmetry out of this. Now, when you look at this, automatically you're going to say the horizontal asymptote is 0 because we have the degree upstairs is 1 and the degree downstairs is 2. So let's go ahead and hit a home run with that one. So HA y equals 0. That is, we have degree. We can say this is d of x, and this is n of x. Degree of d equals 1, and that's clearly less than 2, which is the degree of n. So that's case 1. So that's easy. I mean, the horizontal asymptotes will not give you a lot of grief. Now, what we want to do is say, okay, well, while we're at it, we might as well, in this form, look for some intercepts. Of course, x is 0, even only if x is 0. So x-intercept is just 0. And of course, the y-intercept is the same. We're thinking, is this an odd function? R of 0 is clearly 0. And so now we can go ahead and factor. We have the negative of x, and then we have x minus 4 times x plus 4. But now when you look at this, we see we've got a nice symmetric domain. Symmetric domain. And of course here, if you replace x with its additive inverse, you get the negative of this function. So now we can say symmetric domain, and we have r of the additive inverse of x is actually the negative of r of x. So this is an odd function. Now, just as a little aside, we've got the domain for clear. Let's just review the computation. R of negative x equals the negative of the additive inverse, or the negative of the negative, negative x quantity squared minus 16. So now these absorb, and if you like, you can just kind of pull the negative over and not absorb it. So push the negative over, leave the negative up there, and of course that absorbs x squared minus 16. And of course, this is the negative of the original function. So it indeed is odd. So the idea here is that with the symmetry, we have even an additional help to graphing this function. So when we think of odd functions, we think of functions whose graphs are symmetric relative to the origin. So we're like, okay, we can do this. So now let's go ahead and finish it off. If you like, we can just do a quick sign test. So we've got 0, -4, and +4. And of course, all of these are multiplicity 1. So let's check something over here, -10. So of course, we get negative, negative, which is positive, and a negative, and a negative, negative, negative. So overall positive. So this is interesting. So now, above, below, we actually cross at the 0, above, and then below. So we've got plus, well, this is nice, using the multiplicity, plus negative. Now you can check the signs, but since I've taught you about multiplicity, I mean, sometimes I do this, sometimes I don't. I know a lot of students prefer just to check to make sure, but this does give you a little leg up as long as you adhere to the fact that you see that all of these are of power one. That's really important. Otherwise, this quick technique doesn't work. You have to be sure that in some cases you might want to just touch as an even multiplicity as opposed to cross or quasi-cross in the case of the vertical asymptotes. So now we can get a nice picture of this. So now we'll do our 4, 1, 2, 3, 4. Our numbers are good. We can spread things out. So we have x equals 4, remember an equation, and then 1, 2, 3, 4. So we have x equals negative 4. And now, of course, we have the x-intercept 0, and the y-intercept is the same. And of course, the horizontal asymptote is y equals 0. So we've got all this nice stuff here. So just to give a little bit more room here to draw the graph, let's just go ahead and extend that a little bit. So we have y equals 0. Now notice we start off above, but we have to hug. So in this case, we hug above and then hug. And now we're in, and what's interesting in this particular case is that now we don't stay up here. Now we go below. See, notice below. So this is negative infinity, pick up the 0, and then up here. So we really do have to watch the sign test. Pick it up, and then go up to plus infinity. Like we have here to the 4 above. And then on to the other side, we're below. But then, of course, we have to mirror this through the origin. So we know that this piece is here, even if we didn't have this. And here. So now, of course, you're thinking with calculus, we'd be able to do some nice things with this. Figure out the concavity. We've got an odd function. So because it's odd, we have a symmetry with respect to the origin. So we can really get a fairly good graph here without any calculus, even though we're still cheating. Now, one thing you'll notice is that it doesn't appear to have any relative extrema like minima and maxima, relative minima and maxima. And when you do the calculus, you'll be able to prove that. What it appears is this function is always increasing. It looks like it, but that's not a proof. So when you do the calculus, you'll be able to prove that. So this is really interesting. Now, another thing is that it's clearly, in this case, you know, if we think about this, it's not 1-to-1, but it is increasing. You know, so the thing is, when you throw in these vertical asymptotes, they can really kind of mix up things. You know, you have sections of it that are 1-to-1, you know, but just be careful that there's certain theorems in mathematics that only work when you have certain hypotheses. So always be careful when you make assumptions about problems. So this is a nice example of the rational function graph. Now let's do one that has a slant asymptote. We tried one of those before, but we didn't finish it. So here we go. We went ahead and computed the actual asymptote. And let's see, yeah, I'll remind us of that. So let's go ahead and do this one. So we have, let's say, r of x equals x squared minus 2x minus 24 divided by x minus 7. Now, of course, remember before, this was the d of x and this was the n of x. And in this case, we had the slant asymptote. We computed it and we got what? x plus 5. Y equals x plus 5. So there's the slant asymptote right there. And we computed that. So we want to go ahead and finish this off. So now let's go ahead, we've got a vertical asymptote easily. Let's factor this. We can use clearly a -6 and a 4 because that product is -24 and the sum is -2. So we don't have to work too hard for this one. So again, notice we already before determined the slant asymptote as we did in the previous exercise, because again, the degree here was 2 and the degree here was 1. So no longer do we have the horizontal, we have this slant. That is, we have a line that has a non-zero slope. The slope here is 1. So now let's finish it off. X-intercepts. Well, we just have the zeros of the numerator, which will be 6 and -4. And now we need y-intercept. This is a whole lot easier than doing the rational zeros theorem, but it is fun, and it's going to be a great tool when you get to calculus. So R of 0, again, we'll just go here. When we do R of 0, we get 0, 0, 0. Then, of course, we get a -24 divided by -7. So that's just a 24 over 7. So that's a 3 3/7 if we're thinking about magnitude. Okay, so that's reasonable. Okay, so now vertical, VA, isolated zeros in the denominator. There's only one, it's 7, and it's clearly not a 0 in the numerator. So jackpot, X equals 7. Remember, ladies and gentlemen, asymptotes are equations. So you have to type equations. If you don't, they don't make sense, because remember, we've defined them to be equations. They're lines, so we have to type the equation. Now, when we look at this, we're thinking, okay, let's just go ahead and do a sign test. Let's use this part because it's fully factored. And again, here we go. Multiplicity 1, right? So let's look at the BVs. So we've got -4, and I'll spread this out a bit. We got a 6 and a 7. So we'll just say 6, and I'll spread out the 7 a little bit so they don't get too crowded, all right? So now when we look at this, we're thinking, okay, oh, sorry. Let me just, that looks like a 1, or it doesn't look right. Let me just write it so you can see it. There we go, 7. Now again, notice we've got the factored form, all multiplicity 1. So let's do our friend -10. So -10, we've got negative, negative, and then negative. All negative, 3 negative, negative. And now these all multiplicity 1. So we go to cross, and then 6 we cross, and then back up, but no real cross there. So we've got below, above, below, above. That multiplicity is very useful. So you just test 1 and then use the multiplicity from here on out. Not a bad way to look at it. Now, okay, well, we've got everything. Now we need a graph, right? Let's do the graph. We'll spread this out as much as we can. Now let's see, intercepts, we got a -4. So 1, 2, 3, 4, -4 right there. And then y-intercept 3 3/7. So 1, 2, 3, 4, 5. So 3 3/7 about right there. And let's see, we've got the, let's go ahead and put in the, the other one, 6. 1, 2, 3, 4, 5, 6. And then, of course, the asymptote right here, 7. And now we can put in our slant asymptote. So we've got a 5 here. And then, of course, if we put in this case, a 2, we get out a 7. So about right here. Now let's see. A little more room up there. So here's our line, y equal x plus 5. And so now, notice when we actually do this, we have to hug, pick up. So here we're below. Then we get to the -4, we go above. And then we get to the 6, we go back down. So hug. So we're not really sure how we're going to look through here, but we can just fake it. It may not look this pretty. Of course, I'm doing it so nice here. We don't know how high we go up. We just do a reasonable facsimile. So maybe it goes up a little bit, then comes down, but we're just getting a reasonable graph without calculus. So we need calculus to figure out the maximum here. And then, of course, after 7, we're above, so we can't be down here because we have to cross here. So we've got to be plus, plus. So plus, plus. Right there, hug, hug. So if that's not reasonable for a little bit of work, I don't know what is. The idea is that not right here, again, we're going to need calculus to figure out that relative minimum. And we'll need calculus to figure out the relative maximum. But what's so nice about this particular technique is that it gives us an excellent graph just using arithmetic without calculus. That is, we go ahead and figure out the intercepts, any pertinent asymptotes, and do a quick sign test, and then we have all the information we need. Now, of course, the calculus will provide the minima and maxima. The calculus will provide the shape operator to determine exactly what the concavity is. And what it appears here, it looks like in this case, it's always concave downward, and here it's concave upward. And so we would have to use the calculus to verify that. So what we're seeing with pre-calculus is that when you get to calculus, you're going to use everything you know. You don't want to forget your pre-calculus techniques because they'll be a good way to check your calculus. You do some calculus and then you say, well, does this mesh with the pre-cal that I've already computed? And if it doesn't, then there might be an error somewhere. So you can go back and check something else. So all of this has to mesh together with the calculus, and you'll find these techniques to be extremely, extremely useful. Now, I just want to give you an example of a case where the actual function crosses the horizontal asymptote. And like I said before, you never cross a vertical asymptote, but it is indeed possible to cross a horizontal asymptote. So if you're working on a problem and you're like, does this kind of waver around a little bit? I'm not so sure about this. I need to check this. Let me give you an example of this. And that way you'll be on the lookout for it. So here's an example of where we cross the so-called horizontal asymptote. So example, r of x equals 3x squared plus 6 divided by x squared minus 2x minus 3. Prove that r of x crosses the horizontal asymptote. Well, of course, here I'm assuming that there is a horizontal asymptote, but I think you can look at it and see that. So we've talked about how you compute a vertical asymptote. We've talked about how you compute horizontal asymptote. We've talked how you compute the slant asymptote by division, okay? And again, you can have quadratic asymptotes and cubic asymptotes as the degree of n gets larger and larger relative to D, but we're not really going to spend much time with that. You may see more of that in a differential equations class or in an engineering class or whatever. And so quadratic asymptotes are just as popular as the slant or oblique asymptotes. So it's nothing that we're just leaving out intentionally. It's just that it's not really the mainstay here. But you will see slant asymptotes, oblique asymptotes, as they say in calculus. So what I want to do is just emphasize again the fact that it is possible to cross a horizontal asymptote. So what I want you to do with this problem is to prove that. Well, first off, again, we can say this is d of x, and we can say this is n of x. And so we see the degree of d equals 2, which is the degree of n. So again, this is a horizontal asymptote, and we need the ratio of leading coefficients. So this implies y equals 3 over 1, or y equals 3. That is ratio of leading coefficients. And so if a graph crosses a particular horizontal asymptote, then that means it must assume 3 in its range. And what we've written so far, that has not occurred. Okay. And in most cases, it's fairly clear that it doesn't occur. But when you're thinking, this is an interesting function, it doesn't have any x-intercepts, I think it might actually cross the horizontal asymptote. Again, that's not a proof. Let's just check. So here's a check. So we say r of x question mark 3. Is 3 in the output of r of x? So let's check. We've done some things similar to this before at the beginning of the class, so this should not be odd to you. So we have 3x squared plus 6 divided by x squared minus 2x minus 3 equals 3. So let's cross multiply. So we have, in this case, x squared minus 2x minus 3 times 3 equal to 3x squared plus 6. So again, this is 3x squared minus 6x minus 9 equals 3x squared plus 6. Now, of course, look, the 3x squared terms absorb, and we're left with negative 6x minus 9 equals 6. So let's transpose. So this gives us a 6x, and we have a minus 9 minus a 6. So 6x equals negative 15, which is 3 times a negative 5. And so we have x equals 3 times a negative 5 divided by 3 times 2. The 3's absorb. X equals negative 5 halves. So indeed, 3 is the y coordinate of the input negative 5 halves. So this implies negative 5 halves, comma 3 is an element of the function r of x, if and only if r of x crosses the horizontal asymptote y equals 3. So again, this is kind of a simple calculation, but you can't always assume. Maybe you're doing a graph and you're thinking, I didn't do much work here. There are no x-intercepts. I'm like, maybe I need to check this. So this often happens where you have an unusual distribution of intercepts. And so, like I said before, if you ever think, you're working a WebAssign problem and you look at this and say, let me check that, because there's a graph here and R of X is crossing the horizontal asymptote. Let me check that. Maybe that's the correct graph. So you can always do this algebraically. It's not something you have to guess. And again, what I want you to notice, ladies and gentlemen, is the power of just knowing the intercepts, the sign test, and then of course the asymptotes, because the asymptotes are such a huge part of the graph in the sense that they guide you to the asymptotic behavior. Again, remember, when you have an asymptote and a function, there are values in the domain for which the function and the asymptote become arbitrarily close. And that's why when we draw these functions, I say hug as opposed to arbitrarily close. That's the whole idea about the behavior in the neighborhood of an asymptote. And so when we say asymptotic, that always means that two objects, namely curves, are getting close together. There are other ways to describe asymptotic behaviors. But normally when you hear of them in mathematics, they are regarding functions, okay? The idea is that we often think of certain functions as being asymptotic at infinity because just like here, the values start to get very close together. So even though the word is a little bit strange, I think what you can see here is that we have a certain degree of flexibility with the rational functions. And because of the existence of the asymptotes, we can actually get graphs that are just as simple or even simpler than those of the polynomial. So again, remember with the polynomials, we're looking for multiplicity, we're looking for intercepts, and the multiplicities help us with the sign test. So with the rational zeros, basically we just add a couple of more objects, excuse me, the rational functions, we add a couple more objects, namely the vertical, horizontal, or possibly slant asymptotes, and this toss that in the mix. So we can see how understanding polynomials really give us a leg up on the rational functions. So I hope that what I presented has been fairly clarifying for you, and that hopefully a lot of this is pretty much review. The main thing about the rational functions is to have a good, solid understanding of what's going on. And if you have to be a little bit more fastidious about certain parts, you can always do that. But the mainstay is just like when we're doing factorization of a polynomial. We just use the tools that are available to us and then move the problem forward. So this concludes the material for week 5, and the material that we'll start on after this will be the basic exponential and logarithm functions. Now, again, just like what we've done with the polynomials, all of this will be review, and I'll add a few things to help you build your knowledge base and maybe take you a little up to another level. But again, just remember all of this part of the first part of the pre-calculus is to basically give you a thorough review of the college algebra. And that's what hopefully gives you a better understanding of that material. And then of course, once we get through this, we'll jump into the trigonometry. And because you feel comfortable with the college algebra, you can apply the college algebra to the trig functions. I think you'll like trig when we get to it. But I hope that, again, this has been illuminating, and I appreciate your listening and your watching the video to get your content where you need it to be. So thank you very much. Again, stay warm. We're out of the worst of it. Power's back on. Hallelujah. Boy, I think that I don't want to go through that again. But you know what? As my parents always say, the hard parts of life make us stronger. But I think now we could all take a little bit of a break. But again, good luck as you study, and I wish you well through the rest of the week. Thank you.